Welcome to Chopra's School of Physics. Our today's topics will be regarding electrostatic potential and electrical potential energy, and then we will think of applying in atom or the nucleus how to get the value of the radius of nucleus. So these facts we will discuss after discussing electrostatic potential and electrical potential energy. So first of all, we must be acquainted with the definition of electrostatic potential, and that we have to use some conventions or we have to make assumptions. So first of all, we must know that electrostatic potential is always calculated at a point electrostatic potential is always calculated at a point within electric field, and electric field is generated by a stationary source charge. Any point outside the field is supposed to be infinity, and any charge placed at infinity will have zero energy. That charge will not come itself into the field. We have to do some work on that charge, and that work will be stored in that charge in the form of electrical potential energy. So when that charge comes in the field, the given charge or the source charge exerts force. So now it can be more clear from the diagram. So now I am drawing a diagram and we'll discuss potential on the basis of that particular diagram. I have mentioned here charge Q. This charge is a source charge. Around the source charge, we draw a boundary. Now this whole region around the charge is supposed to be electric field. So this charge has generated electric field. A point is selected within the field, say point P, and other point is selected outside the field, and this point is A. Now a test charge Q naught or unit positive charge positive charge like this is kept at this particular point. This point is outside this field. So this field was generated by Q. It will exert force, but that force will be only existing within this particular region. This is the region around this electric field. So this charge is outside the field. This charge will not experience any force with respect to this electric field. Now this charge is at infinity. Any point outside the field is supposed to be infinity. Here, this particular point or this charge which is situated here, say unit positive charge, it will not move from A towards P itself because its energy will be zero. So I will mention here, energy of a charge at infinity is always zero. Infinity is not subjected to a number. it is that particular point which is outside the field. To carry this charge from A to P, some work will be done on the charge. Charge has got some mass. We can't expect that charge is there and it has no mass. Every charge has got some mass. So once more I will be repeating. That is when the charge will come to position P, this charge will repel it, but it will not go back because it is having some electrical potential energy and that will work against the repulsion of source charge. Therefore, the work done by that electrical potential energy against the repulsion, that is called potential. So V is supposed to be the potential. I'll just mark it separately, V potential. So what is V now representing? V is the potential at a point P, and this is the potential, that is the work done against the repulsion of source charge Q. Now, this potential is calculated again by Coulomb's law. So potential is work done. Work done is electrical potential energy, and work is force into distance. Force is electrical force. This force is existing between the two charges within electric field. So potential where at a point P, that is work done, that is equal to electrical potential energy. This is equal to force K multiplied Q1 Q2 divided by R square multiplied by R. So R we have taken here, and force, this is the Coulomb force between the two charges. R will cancel off and the remaining number will be V equals to work done, electrical potential energy, that is K, and for Q1 we can compute Q, and for Q2 we can compute 1 because we are bringing unit positive charge from infinity, and that is divided by R. So net formula K Q over R. Now the whole thing, the whole concept is that finally we are using again Coulomb's law of electrical force. Wherever we use K as a constant, it means we are using MKS or the SI system. So our assumption was Q is a source charge, around the charge is a field, there is a point within the field, and at this point we have to bring unit positive charge, and unit positive charge is situated at infinity. Any point outside the field is called infinity. This unit positive charge will behave like a test charge. Unit positive charge means 1 Coulomb charge, and energy of charge at infinity is supposed to be 0. Some work is done on the charge, that is stored in the charge in the form of electrical potential energy. Now when this charge comes to position P, Q charge will repel it, but it will not go back to position A because it has electrical potential energy. That is, you can say like that we have given some glucose to this point. So now it will work. That glucose means energy that will work against the repulsion. So we will find that work done is due to electrical potential energy. At this point, whatever work is done in bringing unit positive charge against the repulsion of Q charge, that is called potential at this point. This is calculated according to this mathematical formula. Potential is work done. Work done is electrical potential energy, and this is given as work done force into distance. Now force we have computed, Coulomb force, K Q1 Q2 over R square multiplied by R. R cancels off and the formula will reduce to K Q1 replaced by Q, Q2 is replaced by unit positive charge. So the net formula is KQ by R. So potential is calculated. Potential is calculated by formula KQ over R. K can be written as 1 over 4 pi epsilon naught Q over R. So this is the formula applicable to air or vacuum. That is free space. This potential we calculate in volts. Charge will be in coulombs. R will be in meters. And K, which is 1 over 4 pi epsilon naught, that is equal to 9 into 10 to the power 9 into 10 to the power 9. That is K. 9 into 10 to the power 9 Newton meter square per Coulomb square. To get this value, we will compute the value of epsilon naught as I have explained in my earlier lectures. It is 8.854 10 to the power minus 12. So this will be K is 9 into 10 to the power 9 pi 22 over 7 or 3.14. Now V is estimated in volts, and if we have to apply it to any other medium, then we should take like this. That is 1 over 4 pi epsilon naught epsilon R Q divided by R, or V is equal to, this is for any medium, general formula, or it is K over epsilon R Q divided by R. So here all the calculations will be in volts, and it is KQ by R, R meters, Q coulombs, K 1 by 4 by epsilon naught, this much, and it is divided by epsilon R. Epsilon R is dielectric constant of medium in which experiment takes place. So dielectric constant, if it is air, it will be 1 and the formula will reduce to this number. But if it is water medium, it will be 80 because the range of dielectrics will be from 1 to 80. If it is some other medium, that dielectric must be given. We will compute that and we will get the value of potential. So I hope that this concept is clear to you. This is the work done to bring unit positive charge from infinity to a point in the field. In the field, it will maintain position because of its electrical potential energy. Now in CGS system, V is equal to Q over R for air medium, or V is equal to 1 over P Q over R. P dielectric constant. So symbol is different from epsilon R, but it is dielectric constant, and for air medium P is taken as 1 and the formula will become Q over R. Here V is estimated in electrostatic unit of potential. Charge must be taken in ESU of charge. R will be taken as in centimeters. So 1 ESU of potential. Now normally rule is that MKS units are bigger as compared to CGS, but this is one exceptional physical quantity where MKS unit is smaller and CGS is bigger. So this is an exception, not a rule. So we will say that is 1 electrostatic unit of potential, that is equal to 300 volts, or 1 volt, that is 1 over 300 electrostatic unit of potential. So this is all about the units of potential, and we have discussed how to estimate potential in a field. And another thing, what is electrical potential energy, that we have seen here in this equation. Electrical potential energy means instead of unit positive charge, some other charge is brought. So whenever we have to find electrical potential energy, the electrical potential energy is simply the work done, and work done is F into R, where F will be taken as K Q1 Q2 divided by R square multiplied by R. R will cancel off and the formula will become K Q1 Q2 divided by R. So here in this case Q2 is brought from infinity. Instead of unit charge we will write Q2. Q1 is a source charge. So when the formula will be K Q1 Q2 by R, Q1 is supposed to be the source charge and Q2 is brought from infinity, that is from outside the field. Now this is calculated in joules. So EP is this much, or otherwise we can write this formula as 1 over 4 pi epsilon naught Q1 Q2 divided by R. We have estimated it in joules. The value is for air medium. The medium is air. If it is some other medium, then EP will be written as 1 over 4 pi epsilon naught epsilon R, and it will be Q1 Q2 divided by R. This 1 by 4 pi epsilon naught is K, so formula can be written as K over epsilon R Q1 Q2 divided by R. Or it can be written as, in other one, that is 1 over 4 pi epsilon, that is epsilon naught, epsilon R, that taken as epsilon, and along with this Q1, Q2 divided by R. All calculations will be in joules. So this is how we estimate electrical potential energy, and the series formula of electrical potential energy. This is series, that is simply Q1 Q2 divided by R, and this is estimated in ergs. 1 joule 10 to the power 7 ergs, and 1 erg is 10 to the power minus 7 joules. So I hope that whole concept of electrostatic potential and electrical potential energy, how to use them in the numerical aptitude and their calculations is clear to you. So now I will request you that if you have liked this video, please subscribe. Thank you very much.